Okay, hi again. Dr. P here, and in this lecture we're going to take a look at the E2 reaction. So the E2 reaction is second order. It has a bimolecular rate determining step. So the rate determining step is the collision of the base and the substrate. In other words, it's the deprotonation. And for the mechanism, a typical mechanism would be something like this. So let's say we had H3C, C, let's draw it out this way. C, H, 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 C, H, H, B, R, NaOET, TOH, we get C, H, H, double bond C, H, H, plus Br minus. All right, so what's our mechanism? Well, we have our alkyl halide here. And then we have our base, which in this case is ethoxide. So O, E, T, lone pair, lone pair, lone pair, negative charge. And what we're going to do is we're going to pull off a proton, and then those electrons from that CH bond kick down. And this is one of the cases where you'll draw an arrow that ends at a bond, because these electrons are now adding to turn that single bond into a double bond, and then the leaving group gets kicked off as well. So that's going to give us ETOH plus HC, H1C, HH plus Br minus. Now, one question you may be asking yourselves, or maybe you're not, I don't know. One question is, which of these three protons gets picked off? Well, let's look at this from a different perspective. Let's look at it this way: C, C, Br. Let's look at it in 3 dimensions. Okay, and in this case, our base is pulling off our proton, and notice that, let's maybe circle this in blue, the bromine, the 2 carbons that will form the alkene, and the hydrogen are all in the same plane. We call that coplanar. And then the bromine and the hydrogen here are what we call anti-coplanar or anti-periplanar. All right. Another way to look at this is to look at the Newman projection. So if I cite down this line here, I'll have hydrogen. There's my carbon in the middle. I'll have hydrogen and hydrogen. Then I'll have my back carbon. I'll have the bromine down here. And then I'll have hydrogen, hydrogen. And you can see now that we've got the hydrogen, the 2 carbons, well, 1 hydrogen, the 2 carbons, and the bromine all in the same plane. And again, these guys are anti-coplanar. So what's going to happen is our ethoxide is going to pull off the anti-coplanar proton. You can almost think of it like once the anti-coplanar proton is pulled off, those electrons do a kind of SN2 reaction, and they'll attack the backside of the carbon that has the leaving group and kick off the leaving group. But instead of doing a substitution, it's an elimination because we pulled off that proton, and then these electrons did something like an SN2. So an E2 is sort of the elimination equivalent of an SN2 reaction. Okay. Now, notice there are some interesting details here, I should say, and let's maybe take a look at some of those details. Where's last time we looked at this reaction here. So why don't we check that out again? So let me write it out here. So let's look at this reaction. Let's look at boom, boom, boom. And then we'll have, I guess we'll have it like this. Br, and then NaOET and ETOH. We get our major and minor products there. Now last time we talked about Zaitsev's rule, but let's go ahead and maybe take a look at this from a little bit different perspective. I have a model here, and so here is the 2-bromo, the R2-bromo butane. And so what's going to happen is we will have, I'm going to turn it around this way, we'll have our bromine anti to one of these hydrogens. So this hydrogen will be, whoops, there we go. This hydrogen will be pulled off. And then the electrons, these electrons go down to make the double bond and kick off the bromine. And notice how when we did it that way, we end up with, so that's our new double bond, we end up with a trans product. So let's draw what that looks like, and then we'll draw what it looks like for the cis product as well. And we'll see another reason why the trans is major compared to the cis. All right, so let's go ahead and let me redraw this guy. I'm just going to flip it over. So I've got boom, boom, boom. No, that's not right. Hold on here. Yeah. So I'm just going to flip it over. So boom, 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 boom. BR. 1, 2, 3. Yeah, that's still R. Okay. And then I'm going to rotate this guy because, you know, if I look at these, I've got 2 hydrogens here. So either one of those could be pulled off. So I've got 2 possibilities. One is I have H, C, C, Br. And so if I rotate this to make that guy down, this guy comes out, so I've got my CH3 here, and then I've got a hydrogen, and then on this side I can rotate this to make either of those hydrogens, either of these hydrogens anti. And so let's say I made this front one anti, that means I had to rotate that way, so I'll get my CH3 here, my hydrogen back there, or I could have the hydrogen in front here, and the CH3 is in back. And now if I have my base, let's just say I have hydroxide, that comes in, and we get our elimination here. I should probably put in my lone pairs here on my bromine. Elimination, boom. We get, in this case, we're going to get C double bond C, and these guys are both sticking out, so they'll be on the same side. So this is how we get the cis product. And this guy is going to give us the trans product. Okay, and these are just different conformations of the same molecule. Okay, and so if I look at it like this, I've got, I can do it this way. So hydrogen, carbon, carbon, bromine, and when I pull this guy off and I get the electrons coming down to make the double bond, I'll end up with cis. If I have this guy instead, I'll end up with the trans. Okay, and looking at the Newman projection can help with that as well. So let's look at the Newman projection here. I've got H, so I'm looking down that bond, CH3, back I've got bromine is down, CH3 is over here, and H, and then here, H over here, CH3 there, Br, H, no, sorry, CH3. So you can see that these CH3s are on the same side, so this is going to give us the cis product, and this will give us the trans product. What's something else that you might notice? So look at these for a minute. Feel free to pause and stare at them for a while. Now that you've stopped pausing, what do I have here? I have a gauche interaction. Whereas these guys are anti to each other. So this is higher energy. So for cis and trans possibilities, if you could get either one, some of the product ratio is determined by the stability. Trans is more stable than cis, but some of it is actually determined by the stereochemistry of the reaction. Okay, remember, we need to have a proton that is anti-coplanar to the leaving group. Now, how do we know that this is the case? Well, the evidence for the mechanism comes from the following. Okay, if we look at the following molecule here, if we synthesize the R-bromo, the R2-bromo butane, and we treat this with NaOET, what we end up getting is trans, and that happens fast. Now, if we do the same thing, but use one with the, I guess actually these are, this is chiral, this carbon's chiral as well, because it has 4 different things, because hydrogen and deuterium are different things. But if we do the reaction with the one that has the hydrogen and the deuterium switched, so let me just think here for a second. So I think this one must be R, and this is SR, I think. Anyway, with these guys switched, when we treat this with NaOET, and I'm not bothering to write in the solvent, that's fine, we get the same product. I'm sorry, that should not be H. We don't get the same product, sorry. We get a similar product. But the reaction is slow. So D equals deuterium, which is hydrogen that has a proton and a neutron. Okay, so what this is saying is that we know this mechanism's right because if we have this anticoplanar arrangement, this will be more stable, having the methyls anti instead of having them gauche to each other. So we'd remove whatever proton is anti to the bromine. In this case, it's a proton. In this case, it's a deuterium. We refer to this as the kinetic isotope effect. And it has to do with the fact that deuterium has an extra neutron. So a reaction is slower with a heavier isotope, slower with D than with H. Okay, so the fact that we see this difference means that we're getting different things being pulled off. Okay, hydrogen versus deuterium by the base. But you know, the reason that they're different ones, the reason why we don't have hydrogen pulled off here is if we got it in the conformation that would let us pull off the hydrogen, our methyls would be gauche to each other and we would get the cis product. So it's really pretty interesting, the SN2 reaction. And you can actually look at cases where let's see here. How are we doing on time? All right. Well, you can look at cases in, for example, substituted cyclohexanes. So let's say we have a bromine here, and then we have a methyl here. And we treat this with NaOET. We will get as our major product we'll get this, and as our minor product we will get that. But if we took the similar we took the diastereomer there, so the only difference is the position of the methyl group. Instead of being up, it's down. We only get that product. Now, why is that? Well, don't forget where our hydrogens are. So I have a hydrogen going back like that, and over here I have two hydrogens, one out in front, one behind. Here my hydrogen is sticking out in front, and then I've got, of course, one in front here and one behind there. So if we think about it, this bromine and hydrogen are going to be sort of on the same side. So here we can get an anti-coplanar orientation of the hydrogen and the bromine, and here we can't. So if we drew our chairs, it would look something like this. It's kind of rough there, but there's my bromine is up. That's on carbon 1, carbon 2 here. I've got CH3 that's up. And then I've got my proton here is down. Here I've got proton up, and then a proton down as well. So my bromine and my hydrogen are anti-coplanar. All right, so that's a nice ready-to-react conformation. For this guy, let's look at its structure. I've got my bromine up, but now my methyl here is in the down position. So now my hydrogen's up. Here I've got hydrogen down, hydrogen up. And these guys are not anti-coplanar. Where's my anti-coplanar hydrogen? It's that guy down there, which is, of course, that guy over there. So here we can get a hydrogen that is anti-coplanar that allows us to get the more substituted product. And the other isomer, we can't remove this hydrogen because it's not anti-coplanar. It's not even coplanar, let alone anti. Okay, the bromine's coplanar with the methyl, so that's just not going to work. But there's a hydrogen going the other way over here that is anti-coplanar, and so we'll end up getting this as the only product. We just can't make the more substituted product. So I kind of like these questions, and let's see here. What else do I want to mention about this? Let's see. Oh, the other thing that you might run across is cases where you get the Hofmann product. How do you get the Hofmann product? So I've shown you the mechanism for E2, some details of the mechanism, some reasons why you get different major and minor products. But let's take a look at when you would get a Hofmann product. Okay, so let's go ahead and take a look at, and let's see here. I'm going to go ahead and do that. I'll do carbon, hydrogen, 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 Br, hydrogen, hydrogen. So if I treat this guy with NaOET, I will get, let's see here, I'm going to go ahead and do that. I'll do carbon, hydrogen, hydrogen, hydrogen. So if I treat this guy with NaOET, I will get, I will get as my major product. So that's my Zaitsev product. But if I treat this instead with TBUOK, or KOTBU, I will get, as my major, whoops, sorry about that, major, I will get the Hoffman product. So our choice of base matters. Why? Well, the reason is that T-butoxide, NaOTBU, is a bulky base or a hindered base. So what does our T-butoxide look like? Well, got my minus there. I've got a CH3. I've got CH3, CH3. So these guys are all, these methyl groups are all kind of large, and they can make this basically bigger. And it's harder to get in close to remove one of these protons. So the easiest proton to remove is the one that gets pulled off. Okay, so our Zaitsev product is the more stable product. The Hoffman product forms more readily or more easily. Essentially, because this is big, it requires more energy to get in there, so we have a higher activation energy. And it's just easier, lower activation energy, to pluck off one of those protons that's hanging out over there. So T-butoxide, which is this guy here, is an example of a hindered base. Another hindered base, so this is T-butoxide. Another hindered base is with Li plus there. This is LDA, lithium let's move that up there, there we go. Lithium diisopropylamide, which is actually overkill. It's a super strong base, which we really don't need here. Just use T-butoxide, and these will give the Hoffman product. Now, they're usually not nucleophilic, except, so these guys usually won't do an SN2, but they could on something like a methyl halide. We do have some bases that are non-nucleophilic. And let's see if I can draw these guys here. N, boom, boom, lone pair, boom, 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 and boom, boom, lone pair. So this is called DBU. I don't remember what it stands for. And then we can also have DBN. And these are non-nucleophilic bases. The reason why is that once they deprotonate, they will form a resonance stabilized conjugate acid. And I can show you that in office hours some other time. But these are non-nucleophilic bases, so if they were to add in as a nucleophile, you'd get a positive charge and it wouldn't be particularly stable. But when they simply deprotonate, you can get a resonance stabilized conjugate acid. These are bulky as well. You can look at them. They have these big rings. So these would possibly prefer the or they would possibly form the Hoffman product preferentially. But usually your best bet, just use T-butoxide if you're trying to get the Hoffman product. All right, so that's the E2 reaction, and I know I went into quite a bit of detail there. In the next video, we'll take a look at the E1 reaction, and then maybe do a little bit of a summary as well. So until then, stay safe out there. Bye now.